Hello, everyone. I'm Dr. Jim Daly from Daly Manufacturing. Today, we're going to be talking about proteins. A lot of times, people think about protein as just, these powders that all the bodybuilders take, and uh, protein's what muscle's made out of. So that's what it's for, is to make muscle. And while that may be partially true, there's a whole lot more to protein than just that. I won't diminish that aspect of it, but really we need to look beyond that when we're thinking about the benefits of protein. And first of all, I want the people here, most people don't know much beyond what I said about what protein is and what it does. So we're really going to start with some very basic stuff in protein. It may be kind of complicated for some people to grasp at first. If it is, just sort of hang on. I'll try to make it uh, very simple, and we'll see how I succeed. But let's get into this. First of all, just kind of an agenda. We're going to talk about sort of an introduction to proteins and amino acids. We're going to talk about how they assay methods, and that's kind of a little bit may seem strange to you, but there's a reason for that. I want you to understand how they arrive at protein requirements. Um, Plant versus animal proteins, peptides, amino acids, signaling molecules, health implications of proteins and amino acids, food sources of proteins, and the role of proteins in human health. That's kind of the outline of this topics we're going to have today. It's pretty big, so we'll keep moving. Um, and first of all, what are proteins? Well, they're composed of amino acids. Okay. And most of you are familiar with at least some amino acids. We all know about leucine, that's one we sell here. Lysine, most people are familiar with. Tryptophan, people take to help them sleep. Uh, Arginine, you've heard people talk about using that probably for nitric oxide production. So, we're familiar with some of the amino acids and what they do as uh, simple amino acids, but there's actually 20 amino acids that are used to make up proteins. And uh, proteins are just long chains of amino acids hooked together. That's all they are. And how they're hooked together and which ones go where is what really determines who we are, what we look like, really, whether we're a dog or a person almost, because we're all made of the same basic building blocks. Um, the proteins have four levels of structure. They look really weird when you see the pictures of them. I think I've got one a little bit later, but primary structure is just the chain of amino acids. The secondary structure is how they make coils or what they call beta pleated sheets or one another, but how they make a little more structure to them. And then tertiary, they start coiling around and making weird shapes. And then quaternary, you know, they actually combine together and make bigger protein molecules, separate proteins do. So functionality is determined by their structure. And if you interrupt that structure just a little bit, you make a protein oftentimes not work. Enzymes, for instance, are proteins, and they'll lose their enzymatic activity if they're just changed a little bit. When you take an egg and you whip it, it makes that frothiness. That's denatured proteins. The protein basic structure is there, that primary structure, but they become denatured now. The tertiary structure is gone, and probably a lot of the secondary structure, and they no longer function as enzymes. That they're gone. That's one reason why when we take enzymes orally, um, they don't get into you have to be careful. You'll lose a lot of activity from them pretty quickly. So you want to get them in and to their target in the gut without too much delay, because it is easy for them to lose their activity. when they're secreted in the body, they're actually secreted in a form that's got little sections on each end of the protein. The enzyme is protein, the enzyme protein that keeps them from being digested. And when it goes into the stomach, for instance, they'll knock off those little sections and then they can do their job. But they would lose it, they would be done for pretty quickly without that system in place. So, enzymatic functions of proteins. Here's they have a lot of different functions. It's not just building muscle. They're enzymes. Proteins act as enzymes that facilitate biochemical reactions in the body, digestive enzymes, metabolic enzymes, all kinds of enzymes. Also, some of the hormones are proteins. And function as hormones. Think of human growth factor as one of them, for instance. There are also structural components, and that's what we really think of when we think of proteins most of the time. You think about building muscles and cells and tissues, and that's is where most of them are go. Most of the protein in the body is structural. And then there's transport proteins. These are proteins that bind to different molecules and get them across cell membranes or transport them in the blood, various things. One of these is the alpha tocopherol transport protein in the liver. When you absorb vitamin E, it's the vitamin E is alpha tocopherol. The liver actually has that transport protein there to bind to it so it can be carried around the body to different cells to be taken up into those cells and where it can act as an antioxidant. And without that, you wouldn't have any vitamin E activity. And that's one reason why the other kinds of vitamin E, the gamma tocopherol, beta tocopherol, those things, they don't have any activity because they don't bind to that protein. So they don't function as vitamin E in the body. So it's that's an important role of proteins too that you may probably never thought of before. Now, sometimes we'll talk about proteins and peptides. Peptides, the only difference is proteins are long chains, peptides are short chains. We'll make it simple. Now, the amino acid composition can be a little different, and their arrangements can be a little different. And they can have different biological activities compared to proteins. But basically, they're the same thing as a protein, except they're just shorter for our purposes here. Now, there's different types of amino acids when we get there. So we have what you call essential amino acids, and this is important because proteins have both essential and non-essential amino acids. Now, what's the difference? Essential amino acids are one that must be obtained through the diet or supplements or somewhere. And they play a crucial role in bodily functions in making proteins. Non-essential amino acids are ones that can be synthesized by the body. They are important for protein synthesis and metabolic processes also. Now, there are a few that are conditionally essential, and probably most of them could be, in a way, essential at times. For instance, we know that one reason in glutathione we have glycine in there along with the leucine is that in making the glutathione molecule, we usually give the N-acetylcysteine for that, but N-acetylcysteine is actually, when you give it as a supplement, not the limiting factor. A lot of times glycine, which is not essential, becomes limiting. There's a lot of research on that. And then leucine we put in there with it to help with the metabolic benefits of leucine. So we have those three together, but the glycine is the only one that's the non-essential one, but it's there because it does become rate limiting in making the glutathione at times. Um,
If you hold on one moment, Dr. Jim, I think we've lost your video, your share screen.
oh, really?
I can still see it.
Okay.
Can you see the share?
I can, this meeting has been, as far as I can tell, everything's working normal. I can't see anything different. So what are you not seeing?
We're just not, I'm not seeing the share screen.
Yeah, I see types of amino
Says you are
acids.
screen sharing. Wonder why you're not seeing it.
That is odd.
I see it also, Jonathan.
Weird. Okay, continue on then.
You see it? Okay. And then I'll just point out the basic structure of amino acids. You'll see this is an acid structure up here. It's all amino acids. This is the amine area here. And then all of them have a side chain. Some of them, it can be just simple as an H. But anyway, that's where they differ is right here. This part, these two parts are always the same in all of them. Now, some of them, like proline that makes a ring structure, it's hard to see it, but it's there. So now when we do protein assays, there's lots of different ways of doing them. And it depends on the situation you're in, which one you use. There's research applications that use different methods. There's clinical diagnostic methods too for looking at different proteins. And I'm not going to get into all the different testing methods. Food industry testing uses a little different from most of the others. And it uses an old test assay that was really invented in the 1800s, the Kjeldahl test. It's really one that I've used a lot, actually. You put a food sample in a container like this with a lot of sodium hydroxide, and you just boil it in it. It's a really nasty mess. And then you condense it and it comes in here. And then you basically use what you call a titration to determine the amount of nitrogen in there. You multiply that nitrogen by 6.25, and that gives you the protein in the sample. It's really quite accurate. You kind of wonder at first, how could that be accurate because of all different sizes of proteins, but they kind of average out to where that's really just about dead on almost all proteins. There's a few that not quite as accurate for, but not many. And usually in foods, it is very accurate. And we'll talk about that a little bit later because it's kind of what you're really measuring here is not protein, but nitrogen. And then you're extrapolating from that how much protein is there. And almost all of the nitrogen in these samples are from protein. There are a few other nitrogen containing molecules, but they don't amount to a lot. And so this adjusts for that. Now, there's nutritional differences in proteins. And actually, one of the things that you look about, animal proteins are a complete protein in that they have all the essential amino acids needed for health. And in the basically the same ratios as what you need, not a whole lot of one and a little bit of the other. So that's the advantage to animal proteins. Plant proteins, many of them don't have them in the same balance that animals, people need. They have a little bit different amino acid balance, and some of them may not have one amino acid at all or very little of it. So that's why when that occurs, it's called a limiting amino acid. Now, fortunately, you can get around that with plant proteins with careful dietary planning. In fact, all you need to do is have different sources of plant proteins to get a balanced protein. Basically, if you combine grains and beans, you almost always get a very nicely balanced protein out of that. If you have, reasonable amounts of each, that makes the amino acid balance come out just about right. And there's a lot of benefits to it. Plant proteins are linked to lower risks of chronic diseases such as diabetes and heart disease, and for promoting overall health. It's good for the heart. It's good for weight management. People consistently lose or gain less weight on a plant-based diet. It's not huge necessarily, and you can certainly gain weight on a plant-based diet, but overall, people do gain less weight and lose weight easier if they're on a plant-based diet. That's been shown over and over, actually. Now, we were talking about one of the roles of amino acids and proteins is in signaling molecules, and that turns out to be a critical aspect of protein that's often neglected. When we look at protein requirements, they're based on, to a large extent, on nitrogen balance studies. They try to determine what's the requisite nitrogen excretion per day. So how much nitrogen do people excrete per day? It's a little tricky to do that because when you basically you fast for a while and measure nitrogen in your urine and see how much comes out, and then you can extrapolate how much protein you need to replace, and how much protein you need to replace that. It's a little difficult because when people fast, actually they conserve more, so they have to kind of juggle that around and get it right. But nevertheless, they can pretty well estimate about what you require per day to replace a protein that's breaking down. And most of that's coming from muscle turnover, actually, because muscle cells have a turnover, and all cells in the body do. They turn over, and so we're trying to basically match what we're losing and keep it, what we need there. And that's fine to an extent, but it kind of ignores the other roles of proteins, and particularly the role as signaling molecules. We find that these proteins, leucine in particular, the amino acid, and insulin, insulin growth factor 1, they initiate what's called the mTOR pathway. And that pathway really signals the body and tells it to make proteins, to make muscle, to make other tissues. And you can see there it increases muscle protein synthesis. Now, it turns out that when you're young, this system works very well. But as you get older, this system starts breaking down a little bit, and it takes more leucine to activate it, and it's considered to be kind of analogous to insulin resistance, in that you became protein resistant, and you don't have the response for building tissue that you did when you were younger. Now, this becomes important with aging because as people age, they tend to lose muscle mass. And it can progress to the point of being what you call sarcopenia, where you really have a pathological loss of muscle and tissue mass. And it probably goes well beyond just muscle. I think people lose heart tissue mass and other tissues in the body too. So the requirements from protein appear to actually increase as people get older and not decrease. So as of right now, for instance, for most people, they put protein requirements basically indexed to body weight, but most people, the requirements would be 50 to 60 grams per day, but that's probably not enough for a lot of people to maintain good muscle mass as they get older. Probably people in their 30s and 40s, they probably do pretty well with that, but that becomes more difficult with age. So that's one thing we really have to consider is, how much do we need? Not just how much. It's hard to make an overall recommendation for everyone. And this is where we get into personalized nutrition, personalized medicine, and those kind of things. But age does have an effect on this system. Other proteins, insulin is actually a protein, and it's one that, controls that system too. We just saw that. So does human growth hormone, another protein that influences muscle growth, while also regulating metabolism. So, we have a lot of factors here that are dependent on protein activity that really are not given adequate consideration in establishing protein needs, dietary needs, at least in my opinion. So we've really talked about these already, so we'll just keep going. So impact on obesity, protein affects appetite regulation. This method is mediated in part by increased secretion of GLP-1, and I think everybody's familiar right now with the GLP-1 agonists, receptor agonists that are being used for weight loss. Well, GLP-1 itself does that. Now, it doesn't work the same as the medications because the medications that they're giving for as agonists, they keep that system turned on 24 hours a day, 7 days a week. It's almost scary to me. Whereas GLP-1 is triggered by dietary intake, and it is doesn't last forever. In fact, it's pretty short-lived, so it has to keep being triggered. But the dietary intake of proteins does increase GLP-1, and that does have a benefit for weight loss, just not like that medicines do. So weight benefits and improved body composition, we know about. Proteins are essential for maintaining blood glucose levels, making them a really critical component of a diabetes-friendly diet. And ideally, that would be plant proteins in this case. Glycemic control and is also one of the effects of protein, and a diet rich in proteins supports overall health and wellness, but particularly in diabetes management. It can also be good for hypertension and reducing it. And whether the benefits are more from adding the plant proteins or taking out the animal proteins, I'm not quite sure. Either way, it does have that, and also cardiovascular benefits. Now, when we look at animal-based protein sources, again, we know that they do have a high value as far as having the right balance of that, of amino acids. These proteins provide essential nutrients, also a lot of vitamins and minerals and vitamins, and complete amino acids. However, legumes are wonderful protein sources. Foods such as lentils, chickpeas, and beans are great. Nuts and seeds are great proteins. Whole grains are good proteins. Oats are particularly good, actually. Combining foods for complete protein intake, though, is very important when you're doing plant proteins. You need a complete amino acid profile in your overall diet. Combining different plant foods helps achieve that. Legumes and grain combination, particularly. And a plant-based diet can provide all essential amino acids when foods are combined properly and promote health. One of the things I really want to throw out here now is that animal proteins, with the exception of fish, really are pro-inflammatory in the body, and low-grade but chronic inflammation is becoming an increasingly recognized important part of overall health. A lot of chronic diseases are related to this. Now, this particular study is in mice because you couldn't repeat that in people, unfortunately. However, in this situation, I think it probably does pretty well mimic what happens in people. They used mice that were given dextrose sodium sulfate, DSS, to induce colitis. You feed that and it, irritates the colon, I guess, or anyway, it induces an inflammation in the colon. So they have a colitis. Now, can be a very serious disease if you're familiar with Crohn's disease or other inflammatory bowel diseases. So they're not great. But beyond that, inflammation in the colon really has a systemic effect as well and causes inflammation throughout the body. In this study, they've fed the mice with induced colitis either a protein or a pea protein or a beef protein. And as it turned out, the pea protein really, actually very little, just very mild colitis in those mice. They had very little inflammation. It really shut it down. It seemed to be more than just taking away the beef part of it. But the beef protein mice had a really pretty severe colitis. And so you can see a difference right there mediated in the gut. And it's an interesting study. If you want to read it, it's available. It's open access, so anybody can go and access it on the internet. It's in a fairly recent study. It's just out, actually. So I thought that was great. There's lots of other studies out there, though. The literature is just full of studies, if you go look for it, on the effects of animal proteins on inflammation in the body. And this is something I think we really have to start paying a lot more attention to. And you'll hear me talking more about it in the future. How do you reduce inflammation in the body? Because that's really feeding into a huge amount of our chronic diseases these days. Now, let's just look at the foods that can be rich in protein. This is kind of giving you a rundown of them here. Some of them, like pumpkin seeds, are really high. Actually, peanut butter is pretty high in protein, but it's also pretty high in fat, oil. So that's the downside of peanut butter. Hemp seeds are great. But of the ones that people really eat a lot of, almonds are good, but these two right here, oats and tofu, are quite high in protein. And those are two great foods that you can eat a lot of. Big bowl of oatmeal will give you quite a bit of protein, really. Um, but combined with tofu, which is a legume protein, you get a really much better balanced amino acid content. So you have a great protein there, combining those two for breakfast. And you may not be used to, how do you use protein for breakfast? It doesn't seem like a protein. You could see that in stir fries and stuff. But you can use tofu in a lot of different ways. This one didn't look as good, but here I made a scrambled tofu that I ate with grits. It was mashed with tofu with onions, garlic, turmeric, which gives it a little yellow color, soy sauce, and a little salt. It was actually quite good and actually tasted pretty similar to scrambled eggs, in my opinion. Now, if you wanted to look better and more like scrambled eggs, you would use the soft tofu. I didn't have any soft tofu, so I just used my, firm tofu, and it doesn't have quite the same look, but it was good to eat. It tasted just as good. Um, so I would like for it to look more like eggs, but it didn't. I used to back years ago make cheesecake from tofu, and it was actually very good. In fact, uh, I took it to kind of a show where we did demonstrations in Knoxville, Tennessee, and had people try it, and they thought it was cheesecake. Actually, it was good. I don't even have that recipe anymore. I can make it again, but I don't eat that much sugar anymore, so I'm probably not going to. At our church in Galax, Virginia, a lot of the members go to help out at a soup kitchen type place for people who need a meal. And they made a tofu substitute for ricotta cheese and made stuffed shell pasta with it. And the people didn't know the difference. Tofu just straight out of the container has very little flavor, although it's packed with nutrients, protein particularly. But you can take that as a base and make just about anything you want to out of it. It's very versatile. Also, I often add daily fiber pro to foods because it has both protein and fiber content. That's one downside of a lot of high protein foods, whether plant or animals. They're not too high in fiber and sometimes they're constipating. So I made the Fiber Pro to kind of offset that a little bit. It's still mostly protein, but it's got some of the dietary fiber into it too to keep it a little bit more balanced if you're using it as a meal substitute. Well, in summary, it's about time to go here. Um, our specific emphasis on plant proteins, the plant proteins contribute to reduce disease risk and improve overall health by providing not just protein, but also other nutrients and fiber in a lot of cases. If you're eating them in whole foods, for instance, the oatmeal, even though it's pretty rich in fiber and protein, is really rich in fiber. It's just a wonderful food, I think. Um, Nutritional value, incorporating plant proteins into your diet enhances nutrition, offering vitamins, minerals, and amino acids necessary for well-being. Those proteins, plant protein foods, give you about everything you need, really. You can eat you don't need animal foods if you really plan your diet well, with the exception of you've got to find a good source of vitamin B12. That's really the bugaboo with eating no animal products at all. If you do that, you need to make sure you're getting vitamin B12 from somewhere and probably a supplement. Plant proteins also promote sustainability by reducing environmental impact compared to animal-based proteins in food production. The calories you get from that you get from um, plants are really have a much lower impact on the environment than do animal foods. Animal foods are pretty wasteful. So, you know, there's a lot that you can say for plant proteins and plant foods as general. And I think most of us realize that a more plant-based diet is ideal for our health. With that, we'll stop here. I think we've gone long enough. And if there's any questions anybody has or suggestions or comments, you're welcome to make them at this point. Does anybody have anything they would like to contribute? I'm not hearing anything from anyone. Okay, well, great. We'll sign off and I hope everybody has a good rest of your week.
Thank you, Dr. Jim.
Thank you.
Thank you.
Thank you.